Hello everyone, welcome to lecture 21 on Mechanics and Materials 1. In this lecture we want to talk about the topic transverse shear. In particular we cover sections 7.1 and 7.2 of chapter 7 of the Hibbeler book. So in order to explain transverse shear and what it is, the best way is to go to the beginning of the semester and start from the scratch and build up towards transverse shear based on what we have done before. So if you remember, the first thing we want to do in Mechanics and Materials 1, or the main thing we want to do in Mechanics and Materials 1, is to find a relationship between deformations and loading. Now, in the first chapter, we learned how to relate stresses to loading. In the second chapter, we learned how to connect strains to deformations. And then in chapter 3, we learned how to connect the stresses and strains together. So basically, there is no shortcut to go from deformation to loading, but you can go through these 3 steps basically to find that, or through these 3 chapters. Then based on that knowledge, we studied axial loading problem. In axial loading problem, you apply a normal force, and then the formula, the key formula that we found there was that the displacement of the beam delta is equal PL over EA. That was chapter 4. In chapter 5, we talked about torsion. Now, in a torsion problem, in contrast to the axial loading problem, you apply a moment, which in this case we call it torque, because that moment is actually a normal moment. So in a way, it is similar to axial loading because you apply a normal loading, but the loading itself is not a force, it is a moment. And then we found the angle of twist, phi would be TL over GJ. Then in chapter 6, we talked about bending. Now for a bending problem similar to torsion, you apply a moment. But different from torsion, you apply a tangential moment. So clearly now you see that we have basically 2 types of loadings. And then each of them could be normal or tangential. Now normal force would be axial loading, that is chapter 4. Normal moment would be torsion, that's chapter 5. Tangential moment is the bending problem, chapter 6. So what we want to do now is to basically fill the last piece of this puzzle and to talk about a tangential force. And that brings us to the topic transverse shear. So the question is, what would be the formula, the key formula for a transverse shear problem? And that relationship corresponds to a loading that is shown in the figure here. So basically you have a beam or a shaft and you apply a force that is no longer normal to the force, it's tangential to the beam. So it's not a normal force, it's a tangential force, and it causes a shear stress. We want to calculate that shear stress. And that shear stress is what we call transverse shear stress. Now, until now, if we had this problem, we would just only talk about the average shear stress. So we always said the average shear stress is simply the whole force V, the whole shear force V divided by area. And that was a fair approximation if we didn't know better. But what we want to calculate now is the distribution of the toe itself, of the shear stress itself, through the cross section. And that distribution is shown here in the figure. So in the figure, you see that the shear stress at the center is larger, towards the ends are smaller. At this point, we don't know that, so we don't have any strong reason to believe that this distribution is correct. But by the end of this lecture, we will see that this is correct, and indeed, we find exactly what is the function of this distribution. Now, this is the shear stress component we are interested in, and it's called transverse shear stress, and connects immediately to the shear force that you apply. But you remember, we talked about this before. If you have, for instance, a piece of material, an incremental piece, this is the same thing I'm showing here, but I show it only in 2D. So if you apply a transverse shear here, so if you have a transverse shear downwards, you would need a transverse shear upwards at the other side to keep equilibrium of forces. But now if you have these two, it would start to rotate it. So in order to also retain the equilibrium of moments, then you would also need two additional shear stresses with equal magnitude. We call these two longitudinal shear stresses. So here in the figure, you can see this is the transverse shear stress, and this component is the longitudinal shear stress. Now, why are we talking about this? It turns out that although we are interested in transverse shear stress itself, we cannot exactly calculate that, but we are able to calculate the longitudinal shear stress. But then we know these are equal, so basically we use this equality as a way to calculate transverse shear. So we calculate transverse shear indirectly. So now you may ask, what is the significance of longitudinal shear stress, or how we can feel it, how we can show that this thing exists? In order to explain that, and in order to show its connection with transverse shear, that if you have a transverse shear stress, you indeed would need to have that, you can think of this fairly simple and intuitive example. If you have a set of boards on top of each other, so you stack, let's say in this case, you stack 3 boards on top of one another, and you apply a force P, let's say exactly at the center. So now you can imagine in these boards, you would have shear forces and shear stresses developed. But if you do not bond the boards together, if you do not glue them together, you can see that they are going to slide on top of one another basically. Now, if you want them to stay on top of each other, if you want them to stay perfectly bonded, you need to basically glue them together along these lines. So this simple example shows that although you apply a force in the vertical direction, you get a debonding of the boards in the tangential direction. And if you want them to keep together, you need to glue them along that tangential line. So that glue that you would use to keep them together, it needs to resist against the longitudinal shear stress. So basically that longitudinal shear stress is exactly what keeps the boards together and prevents relative sliding. All right, so I think this example explains very well that if you have a problem like this, so if you have our simple problem that we talked about, you have a beam, you apply a force, you develop a shear stress. Not only you develop a transverse shear, but you also develop a longitudinal shear stress. And then what we want to do next is to calculate longitudinal shear stress, and then because they are equal, that would also give us the distribution of the transverse shear stress itself. So in order to do that, we look at this picture. The process is very, very similar to what we have done before in bending problem, in axial loading, in torsion. What we do is that we consider a beam under a variety of loads. So you can have, or you may have, singular forces, you may have also concentrated or singular moments, you may have also a distributed load. What we want to do is to take a little piece here, an incremental piece with the width dx, enlarge that, and from the equilibrium of that piece, we want to derive our equations. Now, if you take that piece and you enlarge it, it's shown here. You can imagine, and this is what we have done in the bending problem, you can imagine there would be a moment on the left-hand side and then another moment on the right-hand side. So let's say M prime on the right, M on the left. Now we have learned before that due to these moments, or related to these moments, there are stresses basically that correspond to these moments. And we have also learned the relationship between stresses and moments for such problems. So that would have been our Flexure formula. If you remember, we had sigma equals my divided by I. Well, with a minus sign maybe, because we wanted to show that it is compressive if y is positive and y is the distance from the neutral axis. So we have learned before this one. So we know this section must be in equilibrium, and we know the equilibrium of this section basically makes a connection between the stresses here and the moment, and then the moment of inertia I also comes to the play. What we want to do now is to cut that little increment further at a specific height. So let's call that y prime, and that y prime would be the distance from the neutral axis. And now we want to write equilibrium for that. Pay attention to this. Pay attention that's similar to the previous problems. The cross section here may be looking like this. So it doesn't have to be exactly like a square or rectangle or something. It could be just a usual cross section. But what we want to do now, or if you assume this is like a 2D cut, this would be kind of a 3D view of it. So basically on this upper portion, you would have normal stresses acting, which are shown here. But also at that bottom surface, there would be shear stresses. Okay, and that shear stress, now if you look at it, this is exactly that longitudinal shear stress we talked about. All right, so what we want to do is to write the equilibrium of forces for this picture. You can imagine due to all the forces on the left-hand side, you get F. Here, due to all the forces on the right-hand side, you get F prime in the opposite direction, and then you have tau. So if you multiply that tau by the area here, you would also get a force. Then you write the equilibrium of these forces together, and from that we calculate the shear stress tau. Okay, so this is the same picture basically. Now we write the equilibrium of forces, assuming that the direction towards right is plus. So on the left hand side, the force would be integral over A prime, sigma dA prime. On the right hand side, the force would be sigma prime dA prime integral over A prime, but now it's with a minus sign because this would be in the opposite direction. Okay, so these two are simple. And then the force, the effective force you get at the bottom would be this shear stress times the area of that section. Now, the area of that section would be the thickness T times dx, the width, or that incremental width that we chose. So, and then the direction is towards right, so you would get a force tau times T dx. And then again, this is basically your dA area. So the sum of all these must be 0. That's your equilibrium. The next thing we want to do is to use our flexural formula or flexure formula from our bending analysis. And if you remember that we had the relation sigma equals my divided by I, which basically tells you that the stress distribution is linear and it's 0 at the neutral axis. So this is your relation for sigma, and what we want to do now is to replace the stresses using the flexure formula. Okay, so we do that. Pay attention that this formula before it came with a minus sign to indicate that the stress here is compressive. But we don't have to do that. We already paid attention to the signs when we wanted to write the equations. Okay, so this would be now your equilibrium equation. Now, if you take a closer look, you see there is this term which is similar in these two integrals, and it comes with a minus on the second integral. So you can imagine those two terms will cancel together, and what you will have would be this one. So this would be your remaining part. Also, dm and moment of inertia I, these are constant, so they come out of the integral. So you would have an integral of y prime dA prime over A prime. And then on the other side, you have tau t dx. But the quantity that we are looking for, let's not forget that the quantity we are looking for is tau itself. So we reorder this equation a little to get tau on the left side, and then this would be our relationship for the shear formula. So 1 over IT, T is the thickness again, dm over dx, that is essentially m prime, which if you remember, this would be the same as the shear force V. And then you have the integral of y prime dA prime over A prime, and if you remember, this looks very similar to what we learned as the first moment of area. And that's exactly what we are going to do. So we replace the dm over dx by V, that is the shear force itself. And then the integral, we call it Q, which is the first moment of area with respect to the neutral axis. having that, then we can write our shear formula like this. So tau equals VQ over IT. The only thing you need to pay attention to in this formula, or when you use this formula, is that when you calculate Q here, that is the first moment of area with respect to neutral axis, but this is for the area A prime. And A prime starts from the section you want to know the shear force for. So if you ask yourself, what is the shear force or shear stress, what is the shear stress here? You would be looking at the Q of this area. So whatever is above that line. Okay, so you need to pay attention that you integrate over the area that starts from the distance from the section where you are interested in, all the way towards the upper end of the beam. You also know that if you have an integral like this, we usually just don't calculate it really. For simple shapes, we know what this is and we have tables. So that integral itself, it would be y prime bar, which is the distance of the centroid of that area from the neutral axis, times that area itself. So this is possibly the most confusing and difficult part about this formula. You need to make sure that if you are interested in this, in the shear stress at this specific height, you will be looking into the area that starts from that point all the way up. Okay, in summary, we have this. So this is our shear stress formula. This is our first moment of area. Now, based on this analysis, or based on what we have learned so far, we want to answer that question that we had at the beginning of this lecture. So if you have a beam with a rectangular cross-section, as shown in the figure, and you apply a shear force V, what would be the shear stress distribution over the rectangular cross-section? And for this picture, we know that the neutral axis is exactly in the center. So it's a symmetric cross-section. We want to solve this problem exactly using what we have on the right-hand side of this slide. All right, so basically what you want to do is first to calculate Q. And if you are interested to find the shear stress at the distance y, you would calculate Q for this area, which starts from y all the way up to h over 2. Now, that area itself, if we call it A prime, it's basically this side, which is B, times this side, which is h over 2 minus y. So this is your area. This is A prime. The next thing you need to do is to find this distance, which we call y bar prime. Now, that's the distance from the centroid of that area to the neutral axis. And that distance is half of the height of that rectangle And the height of that rectangle itself, we just had it. It was h over 2 minus y. It's that. So we take half of that height. So that's why you have a factor 1/2 here, plus y itself. Okay, so this distance is half of that height plus y itself. And that's what you see here. Okay, now that you have y bar prime and a prime, you just multiply it and you have this formula, this relationship. Now you can see that your Q, your moment of area, is a quadratic function in y. So if you want to use this formula, tau equals VQ over IT. Now we know what is Q. I is standard for rectangular cross section. It's 1 over 12 BH cubed. T in this case is basically B. It's just the width and it's identical, it's uniform. So we have everything that we need to find the relation for the shear stress. And if we insert these numbers, we would have this formula. So this is your shear stress distribution. And as you can see, it's a function of y. So it's not constant. That's the first thing. The second thing you can see is that it's not even linear. It's a quadratic function. Another thing that you can see is that if y equals minus plus h over 2, shear stress would be 0. So that tells you on top and the bottom of the cross section, the shear stress is 0. Also, if you set the derivative of this to 0 to find where it is maximum, you can see that it would be maximum at y equal 0, which is indeed the neutral axis itself. And interestingly enough, you can see that maximum shear stress from the formula, so if you set just y equals 0, h squared cancels with, let's say, h squared here, and then bh would be your area. 6 over 4 is 1.5. So you can see that your tau max would be 1.5 v divided by a. Now, v divided by a, we call this the average shear stress at the beginning or until now. So you can see that the maximum shear stress indeed is 50% larger than the average shear stress. So basically the shear stress is as shown in the figure. It's a quadratic function, 0 at the ends, maximum at the center, and that maximum is 1.5 times the average shear stress. Now, the fact that the shear stress is 0 on top and the bottom, it makes perfect sense, because remember, we said that the shear stress, the transverse shear stress that you are looking at, it should have a component on the other side, which is the longitudinal shear stress. So in this example on top, this is a free surface. So if you have a free surface, you don't have actually a force applied here to compensate that longitudinal shear stress. So you expect to have a 0 shear stress on free surfaces, basically. So that makes perfect sense. All right, so if you remember the picture or the slide that we started with, we had this, except that here there was a question mark. Now we have answered that. So we know that the shear stress formula for transverse shear problem is VQ over IT. What we want to do next is to go to chapter 8 and to solve exercises together using a combination of all these cases. So you can imagine if you have a problem which looks like a transverse shear, it may closely relate to a bending problem, for instance. Or in reality, you can imagine you would have a combination of these cases happening together. So that is the discussion that we will have in chapter 8, and we call that combined loading. But this slide should give you a very clear roadmap of what we have done in Mechanics and Materials 1 all the way from chapter 1 here to chapter 8. All right, this was our lecture on the topic transverse shear. We covered sections 7.1 and 7.2 of chapter 7 of the Hibbeler book. In the next lecture, we talk about combined loading and go to chapter 8 of the book. I'll catch you in the next one.